All right, Codeforces round 856. Wait. So you just take the two longest strings. I mean, okay. Kind of been a while since I did one of these. A 2 times. Is this right? Because what if both ways work? That's fine. I forgot to run the samples, but I guess it doesn't matter. Oh, what happened? Oh. Yeah, that's what I need. Oh. Wow, okay. Oh, what's that? So what does it look like? I don't know how to. Right, if it's sorted, then I think this is pretty easy. All right, go back to B. Yeah, what if you have one? You have one and like. Oh, you make this. Oh, you make this. Okay, what? You make this one even. You make this one odd. There's gotta be some obvious solution that I was missing. Like even like yeah, if you have one and like 20, it's very long. Oh, you just make everything at least. I see. Okay, make everything at least 2, and then you just go from left to right. If it's divisible, you just bump up by 1, because. Very interesting. Oh, wow, what? You need to find. So you have 2 n numbers, you need to find n primes. You pick n primes and then you can. So for every way. Change the whiteboards. So once you pick the primes, you divide by factorial number. Okay, so just a basic knapsack, I think. I should sort them. Actually, choose this. just makes it 0 every time. Oh, that's why. Oh. Looks like we're good. You can actually do this much faster with NDT. They could have made N way bigger. Yeah. Anyway. Oh, so N squared is really obvious here. N squared is really obvious. But... Maybe hashing? Hashing, because there's there's only n hashes that would be allowed. That's just possible. I go eat and think. Where is it? Oh, of course. Of course. Yeah, I think just do a hash. Wow, that's fast. 7 minutes. Okay, well, that's my plan. All right, and now we kind of need to do this. Oh, okay. I don't think we need all this. Oh, we kind of want this. Oh, we don't need hash pal. That's not necessary. Just two, sure. I don't think I need this. I don't need this. I don't need this. I need this. Yeah, okay. Here we go, reverse. I guess it's 1 because, yeah. Times hash mul h. Yeah, because we're, yeah. So let's compute down hashes, and now we can compute total hashes. Well, we start with this anyway. If that's the case, we're done. Okay. So we're gonna go here. Yeah, we're going to subtract our... Wait. Wait. Oh, do we need to divide? Is it? Yeah, isn't that it? Okay, vector. This is the... Oh yeah, we don't want any twos, technically. This is the goal hashes. Where is this happening? Oh. I guess you can do that, right? Oh, that's not one. Oh, okay, maybe not. I don't know why. Oh. Oh, that's why. How do I make that work? No one else? What? I'm confused. Okay. I see. This one ended with like. Okay, what if I just did this? That would be better. Oh, it's because if I want to do 1, it's annoying. Okay, I want to do 3. Oh, this is worse. This makes the last one 0. Well, anyway. Okay. Yeah, I'm gonna go eat and then I'll come back to explain. All right, so we're back. Let's talk about it. So, kind of crazy. I did all the problems in 35 minutes and I didn't get top 2. That's crazy. These two were very, very fast. But anyway, a lot of people are finishing all 5. And yeah, let's just talk about these. So problem A. So problem A, you got all the prefixes and the suffixes. Basically, you take the 2 longest ones, so the longest prefix and the longest suffix, and you just try to concatenate them together. So if one way doesn't work, you do it the other way. Like one order doesn't work, you do it the other way. So for example, this one you have ABC and BCD. Obviously, the way to combine them is ABCD. There is a case where both versions are possible. But in that case, the string looks like A, B, A, B, A, B, like that. And so you'll get like A, B, A, B, A, and you'll get B, A, B, A, B, which you could combine to make A, B, A, B, A, B, or you can make this, right? But it doesn't affect, ultimately, whether it's a palindrome. Either both of them will be, or neither of them will be. So that's actually fine. There's like, I guess there's some case for like an odd length where you have this version and you can make this instead, but again, whether they're a palindrome is the same in both cases. So that's what we end up doing. We take the 2 longest strings, figure out how to combine them, and then just check if that's a palindrome. That's it. All right, problem B. Problem B is kind of tricky. You have to like find the right way to do it. You want to make AI plus 1 not divisible by AI for every I. What I ended up doing was, and at most 2 n operations. What I ended up doing was, first of all, if anything is 1, you need to bump it to be 2. And so now we can assume everything in our array is at least 2. And then we can actually just, it's very simple, we just go left to right. If AI plus 1 is divisible by AI, we can just increment AI plus 1. And that always works because everything's at least 2. So since this is at least 2, this is 0 mod that. So once we increment, it'll be 1 mod that. And since we go left to right, we're not breaking any of the previous divisibility situations. So that's B. That's it. Take some thinking. There's like a lot of approaches you can take that end up not working, and so you need to find the one that works in under 2, or at most 2. All right, C. What is C? Oh yeah, this one is a little bit funny. It's a little silly. They have all these descriptions, really all you're doing is, because the array is sorted, for any prefix, the only things you'd use are a suffix to get the biggest possible values. And you want to know how long you can keep kind of increasing the value by taking a bigger and bigger suffix. So I just do this via binary search. So for each prefix, I just binary search how long a suffix I can do. To check if the suffix works, we need the smallest thing in the suffix to be at least the length. Yeah, that's it. It's just a binary search on that. It takes a little bit of time to, it takes just a little bit of observations on this function to convince yourself that that is the right thing to do. But once you convince yourself, then it works. Basically, the idea is, as your suffix gets longer and longer, the newest s value is smaller and smaller, but this product on the bottom gets larger and larger. Or rather, the newest value that you add to the factorial, like going from 5 factorial to 6 factorial, means times 6. That value gets larger and larger. So this whole value, once it decreases, it will keep decreasing. Yeah, let's see. All right, D. So D, right, so for D, you can actually solve D with way bigger constraints than this. You can have like n up to like 200,000 and AI up to 10 to the 18th. Because all you end up needing to do is you need to check for whether a number is prime, and then you have a bunch of polynomials that you're going to multiply. And I do that with knapsack, so it's like a n squared, but you can do that with NTT for n log squared n. But anyway, the idea is, once you pick your primes, then the rest of them are exponents, and you just need to distribute them. So you get, it's like a, what's that called? Multinomial coefficient. This thing. So you just take n factorial divided by the individual factorials. And those individual values are how many kind of counts you have for each number. So if you have like, if you have the numbers like 22666, you're going to 5 factorial because they're 5 things, divided by 2 factorial times 3 factorial, because we have one group of 2 and we have one group of 3. And so that's the count we would get. And we could, theoretically, we could iterate that over every set of n primes, but we don't need to do that. Instead, we just know that if we pick this prime, then what happens is we end up replacing that. So for example, if we have like 5 2s, and we decide to pick a 2 as one of our p's, then instead of divided by 5 factorial, we'll have it divided by 4 factorial. So we actually multiply by 5. So then essentially we need to pick n of the primes where a prime that occurs k times is worth times k, essentially. So we get all these polynomials that are like, this one would be 1 plus 5x, right? And if there's like 3 7s, you would have 1 plus 3x. And so we're just multiplying all these polynomials and finding the coefficient of x to the n. I'm doing that here with a knapsack, but yeah, it's just polynomials you can multiply more efficiently. Anyway, that's D. And then finally E. So for E, yeah, we just use hashing. The idea is to use the hash function where hash of a set of distances, D, is just going to be the sum of, we have a fixed value M and P, and it's just going to be sum of M to the D, all this mod P. And this is just a hash that's pretty simple. The point of it and the reason that we set it up this way is because now we can do the operation increase all distances in the set by 1. You just take hash times mod P. And then another thing we can do is we can subtract a set of distances. So like we can cut it in half and remove half of the set. And that's just subtracting mod P. So that's why we picked this particular function. With that in mind, then the rest of it becomes pretty simple. We need to do, I do this with 2 hashes that are 2 32-bit values so that we have a 64-bit combined value. You can also do like, I can also do 3 32-bit values to be even more safe, but 64 bits is good enough in general. So one thing that's tricky is like, oh, you need to do kind of like up and down hashes sort of, because you're trying to have every node as the root. The way you do that is you compute all the down hashes first. So you compute the hash of each node's subtree, and then we're going to compute the total hash at each node. And there's a cute little idea where you compute the total hash at a node x by starting from the total hash at its parent, removing x's subtree. That would be the up hash, and then we need to do that increase distance by 1 operation multiplied by the multiplier m, and then add back our down hash. So that's what I'm doing here. Take the total hash for the parent, subtract our down hash with distances increased by 1, so we multiply. That is the up hash. We take the up hash and multiply it to increase the distances by 1, and then we add our down hash. And that is the idea. And then we have n goal hashes because there's one missing thing. So it's just each possible value of the missing thing gives us another hash. And we're just looking for whether each node's hash occurs in the set of goal hashes. Yeah. All right, that's it. That's it for this contest.